The concept of manipulating matter at the atomic or molecular scale was first articulated by Richard Feynman in 1959 in his famous lecture at American Physical Society meeting at Caltech. "There's plenty of room at the bottom." He imagined building machines atom by atom and writing the entire Encyclopedia Britannica on the head of a pin. He proposed that future scientists could manipulate individual atoms to make miniature circuits and molecular machines. This was a theoretical vision, long before the tools existed. So, nanotechnology was conceptually born in 1959, but it remained a dream for 2 decades. The term nanotechnology was first used in 1974 by Professor Norio Taniguchi, a Japanese scientist at Tokyo Science University. He defined it as, "Nanotechnology mainly consists of the processing of separation, consolidation, and deformation of materials by one atom or one molecule." That was the first formal scientific definition of nanotechnology. Nanotechnology became practically possible in the 1980s, when scientists invented instruments such as scanning tunneling microscope, STM, and atomic force microscope, AFM, capable of seeing and manipulating individual atoms. These tools gave birth to experimental nanoscience, direct observation and manipulation of atoms. In 1985, discovery of fullerenes, C60 buckyballs, sparked massive interest in carbon nanostructures. Scientists Harold Kroto, Richard Smalley, and Robert Curl were awarded the 1996 Nobel Prize in Chemistry for their discovery of fullerenes, which are a novel form of carbon. In 1991, Sumio Iijima, NEC Japan, discovered cylindrical carbon nanostructures called carbon nanotubes, CNT. CNTs have extraordinary mechanical and electrical properties. Since the 1990s development of quantum dots, nanoparticles, nanocomposites, and molecular electronics expanded the scope of nanoscience. During this time, growth of nanomedicine, nanoelectronics, and nanophotonics also supported by the government organizations around the world. Ancient nanotechnology. Even before Feynman, some materials from antiquity show nanoscale structures made accidentally. Among them, pottery shards from India, Lycurgus cup, medieval stained glass, and Damascus steels are prominent examples or early nanomaterials application. Pottery shards excavated at Kiladi, Sivaganga district, Tamil Nadu, were found to have a black coating on the inner walls. Scientific analysis, Raman spectroscopy, TEM, transmission electron microscopy, X-photoelectron spectroscopy, revealed that this black coating contains single-walled carbon nanotubes and multi-walled carbon nanotubes, plus layered sheets of carbon. The average diameter of the single-walled carbon nanotubes was reported as 0.6 nanometers, one of the smallest reported in human-made artifacts so far. The pottery is dated to around 600 BCE, or slightly earlier. The researchers state these are likely the oldest known human-made nanostructures discovered to date. The Lycurgus cup is one of the most stunning and scientifically intriguing artifacts from antiquity because it's essentially a 4th century CE Roman glass nanotechnology masterpiece. The glass changes color with lighting direction, appears green in reflected light, appears deep red in transmitted light. This optical effect is called dichroism, and it results from metal nanoparticles embedded within the glass. In the 1990s, analysis by the British Museum and University of Nottingham revealed the glass contains gold, Au, and silver, Ag nanoparticles. These particles are extremely small, 50 to 100 nanometers in diameter. The metal particles are uniformly dispersed throughout the glass matrix. This nanoscale mixture causes plasmonic effects that manipulate visible light, the same physical principles used in modern nanophotonic materials. The Romans didn't intend to make nanoparticles, but they had sophisticated glass coloring techniques. They added metallic salts or oxides, e.g., AuCl3, AgCl, to molten glass as colorants. During controlled cooling and reduction, metal ions, gold 3+, silver+, were reduced to metallic nanoparticles dispersed within the glass. Firing and annealing conditions controlled particle growth, accidentally reaching the nanoscale range that gives rise to plasmonic color. The steel of Damascus blades, which were first encountered by the Crusaders when fighting against Muslims, had features not found in European steels. A characteristic wavy banding pattern known as damask, extraordinary mechanical properties, and an exceptionally sharp cutting edge. In 2006, a team led by Peter Poffler and Marianne Reibold, Technical University of Dresden, Germany, published a landmark paper in Nature showing that ancient Damascus steel contained carbon nanotubes, CNT, and cementite nanowires, Fe3C. Scientists used high-resolution transmission electron microscopy to examine a sample of Damascus sabre steel from the 17th century and found that it contains carbon nanotubes as well as cementite nanowires. This microstructure may offer insight into the beautiful banding pattern of the ultra-high carbon steel created from an ancient recipe that was lost long ago. It is believed that Damascus blades were forged directly from small cakes of steel, named woots, produced in ancient India. A sophisticated thermomechanical treatment of forging and annealing was applied to these cakes to refine the steel to its exceptional quality. However, European bladesmiths were unable to replicate the process, and its secret was lost at about the end of the 18th century. It was unclear how medieval blacksmiths would have overcome the inherent brittleness of the plates of cementite, Fe3C, a mineral known as cohenite, that form in steel with a carbon content of 1 to 2 weight%, as well as how the steel's characteristic banding could have arisen from these plates. The brilliant colors in medieval church stained glass windows, like those found in Chartres Cathedral, France, or York Minster, England, are actually caused by metallic nanoparticles embedded in the glass. In 1856, Michael Faraday created the world's first gold nanoparticle colloid, a ruby-red suspension whose color arises from surface plasmon resonance. His meticulous study of light scattering, stability, and aggregation laid the foundation of colloid and nanomaterial science, anticipating the core principles of nanotechnology more than a century before its time. Michael Faraday's gold colloids are not only one of the earliest experiments in nanoscience, but also a foundational discovery in colloid chemistry and nanoparticle optics. Faraday was asked to investigate activated gold treated with phosphorus that behaved unusually in chemical reactions. Through experiments, he produced a deep red-colored solution by reducing gold chloride, HAuCl4, with phosphorus in water. He realized that the color wasn't due to dissolved gold ions or ordinary particles, but to extremely small suspended particles of metallic gold. The solution had brilliant red coloration rather than gold or yellow. The color changed depending on particle concentration and light conditions. The gold could scatter light and coalesce, aggregate, when salts were added, showing colloidal behavior. Faraday described these as very finely divided gold particles. what we now know as metal nanoparticles with dimensions in the 10 to 100 nanometer range. The ruby-red color of Faraday's gold soul is caused by surface plasmon resonance, SPR, the collective oscillation of conduction electrons in gold nanoparticles when exposed to light. This interaction depends on the size, shape, and dielectric environment of the nanoparticles. The brilliant colors in medieval church stained glass windows is due to surface plasmon resonance, SPR, the same optical principle behind Faraday's gold colloid in 1856 and the Lycurgus cup during the 4th century CE. In summary, nanotechnology began conceptually in 1959 with Richard Feynman's vision, was named in 1974 by Norio Taniguchi, and became experimental reality in the 1980s with atomic-scale imaging tools. Humans have been using nanomaterials for over 1,600 years, long before they knew it, in glass, metals, and pigments.